Okay, so what we concluded with yesterday was basically that we believe that the antiderivative, if you take the difference between two values, that will provide you with the area under a curve. So we kind of ended our class with some simple examples like this. Well, first we had this theorem, and it was just basically the integral from a to b of f of x dx is capital F of b minus capital F of a, where capital F represents like an antiderivative. Okay, so the examples we did, and especially if you watched the video, you saw examples like this. A really classic one would be like if you wanted to do the integral from 0 to pi over 2 of cosine x dx, right? So we understand this geometrically now. We know that this means, here's a cosine wave. We just want this area. That's all it means. Very simple meaning. And we said that you can actually find it by asking the question first, what is the function whose derivative is cosine? So what did we say? Sine x, right. So we believe that sine x is the key to this problem. And we said that it actually could be sine x plus any number, right? And then you're supposed to take this and evaluate it at pi over 2 and at 0 and do a difference. So typically what people do is they'll draw one or more brackets like this. This bracket, everybody I know puts this bracket on the right in here. Some people draw this bracket I have on the left, some people do not. So some people have it like this. And some people have a left bracket also. It's up to you which you want to use for your notation. Like that. I usually use both. Okay, so you're supposed to plug in pi over 2 for x and also 0 for x. So we're just kind of redoing this example. So sine of pi over 2 plus c minus, and then sine of 0 plus c, which is 1 plus c minus none plus c. In other words, 1 plus c minus 0 plus c. What always happens on these problems is the c will cancel out like that, which makes me regret even using it in the first place. So maybe next time I won't even write that plus c. And this answer is 1. So that just means that the area here is actually exactly 1. Now our calculator gave us that answer a couple days ago, before we even learned this, but we did not fully know that it was exactly 1.0 until just now. This is actually exactly 1. Interesting. Okay? And you can apply this to any function as long as you know how to find the antiderivative. Yeah, question?
Is that how like the calculator solves it? Is that it?
No, the calculator uses like I believe it uses a trapezoidal method, which is section 5.5. Yeah, 5.5. And what it does is it draws little trapezoids in there and it finds the area of all of them, which is a little more accurate than using rectangles. Or it might even use what's called Simpson's rule, which is even more accurate than that. But yeah, the calculator is using more of a less brainy approach. Like it can't really figure out antiderivatives necessarily, unless it's a TID9. Then it's actually programmed to understand all those things. So, okay, but what a powerful little trick. So actually, the first example we did was we just had 3x squared, and why don't we just try to find the area between like 5 and 7. Okay, so let's just revisit this example again. We definitely need to understand this. This is super important. So I just need to know what function has 3x squared for derivative. So that's simple enough. What's that? X cubed. So I'm just going to put that here. I'm not going to put the plus c. Last time that was a waste of time. So x cubed is the function whose derivative is 3x squared. And now I'm just going to plug in 7 and 5 and take a difference. So it's 343 minus 125. That's really simple. Except I don't know what that is. 218, that sounds right. Yeah, and this is the area under the 3x squared curve between 5 and 7. It's a rather large positive area. Okay? So always keep in mind what it means in calculus. Don't lose sight of the meaning of things. The AP test has an excellent way of not only getting you to get the right answer, but also to interpret it properly so you know what you're doing. Okay? Now, you guys are going to have some trouble with certain problems, But this one you should be able to figure out. See if you can figure this one out. So I'll give you 30 seconds. See if you can figure that one out. All right. What is the function whose derivative is 1 over x? That's ln, right? So we're talking about ln, and we're evaluating between 1 and e. So you actually are supposed to do ln of e minus ln of 1. What's ln of e? Correct. What's ln of 1? 0. So this is interesting to me too, that if you look at the graph of of 1 over x, which is a very familiar graph. You should have seen this graph in pre-algebra, okay? Or at least algebra 1. The area between 1 and e in here is 1. Interesting. Not 0.99, 1 exactly. Kind of neat. Okay, any questions on that? Okay, so this just becomes an exercise, like a game, where you try to guess what function gives us this derivative. This game can become very, very, very hard, very quickly. For example, this problem is simple enough. Sine x, this is a really easy one. Okay? That's right. The derivative is sine x, so the function would actually be whatever gives you a derivative of sine x. So can you think of a function whose derivative is sine x? Doesn't cosine x give us sine x when we take the derivative? Yeah, when you differentiate cosine, you get negative sine. Yeah, so maybe if we had negative cosine, that would do it, right? That's the correct answer. I'm playing dumb. The negative, I always act like I don't know, but sometimes I really don't. Can't tell the difference. But negative cosine x is the only function whose derivative is sine x, right? Of course, we could add like 10,000, but we decided that was kind of a waste of time. Okay, let's plug in pi and 0, see what we get. Okay, so we would have negative cosine pi minus negative cosine 0. This is negative of negative 1. And this is negative of negative 1. So this is 2. This is 2. It's 1 plus 1, which last I checked was 2. So this just means that on a sine wave, if you calculate the area of this full bump right here, its area is 2. Interesting. Okay, that one wasn't too hard, but what if I gave you this problem instead? Sine x over x. We've studied this function a lot. Actually, we know the limmo for that. We know that if x goes to infinity, this function shrinks to 0. Maybe some of you know what its graph looks like. It looks something like this. Okay? It doesn't look like an even function, but it is. And it looks just like that. And the question is simple. What is the area under this curve? And yet no human can solve it. Nobody can guess the function that gives us this derivative. Sine x over x. What is that function? Nobody can figure it out. In fact, people have figured out that there is no function that will give us this derivative. Interesting. Maybe you thought it would be like, you know, cosine x on top, maybe negative cosine x on top, and then down here there's like a 1/2 x squared or something. That way when you take the derivative of this, you get sine x. Take the derivative of this, you get x. But that's not how things work. You don't take derivatives at top and bottom like that. You have to use like quotient rule, chain rule, and all that stuff. In other words, this problem's a dead end. And people, everybody uses a computer on this. Even the most advanced mathematician would use a computer on this problem if they want to find the area between, let's say, 0 and 5. Okay, so what I'm saying is there are some problems that will stump us because we can't find the antiderivative. We just can't do it. Unlike derivatives, where we're very comfortable doing the derivative of almost anything. Okay, so I needed to tell you that because sometimes you're going to have to bust out your calculator. It's just the way things are. All right? Guys like Newton wish they had a graphic calculator so they could get answers to these quickly. but they didn't have that option, that luxury. So they had to use LRAMs, and all that stuff was still necessary for them. Okay, any questions on what I just said, how some problems we just cannot find the antiderivative? All right. Now let's say that you were given something like this, d dx of the integral from a to x sine t over t dt. This problem we can solve. Okay? Because what's going on here is we're taking the derivative of the integral. See? So this is not an integral problem, really. This is, let's find the derivative of the integral of sine of t over t. The answer to this problem, by the way, is sine x over x. Sine x over x is the answer. Let me explain why. The integral is asking, this part of the question, if you cover up the d dx, is saying, what function gives us this derivative? I'm actually not too sure, I don't think any person knows. Somebody once made up a name for it, but they just made it up. So let's just say that the function is on a j of t, I don't know. J of t. So now it looks like this, and you're evaluating between a and x. Okay? So you plug in the x, plug in the a, you have basically d dx of j of x minus j of a. Right? But now you can take the derivative of it. So what's the derivative of j of x? J prime of x, right? What's the derivative of j of a? A is a constant. 0. So now you're right back to j prime, which was sitting here all along. Is j prime of x. So it's basically just sine x over x. So what it looks like happened on this, to get the answer, is it almost looks like I just took that upper limit and just plugged it in. Plugged it in for t. That's what it feels like I did. And by the way, that will work. That's how you do these. You just take that right there and you plug it in. Bam. All done. That's really easy. Let's try another one. D dx integral a to x e to the minus x, let's do e to the minus r squared dr. Okay? A is just some number, like a constant. So you would just literally plug in this x for each r that you see. I only see an r squared, that's all I see. So this just comes out to be e to the minus x squared. That's the answer. It's very simple. Okay, so I feel like I should prove to you that that works, you know? So let me just prove that to you. Prove that the derivative of the integral from a constant to x of f of t dt is simply f of x. And we can just simply go like that, plug it in. Why does that work? Okay, so here's the proof. So let's start with the left side of this thing. We believe that this is supposed to somehow turn out to be just plain f of x. Okay? All right, so this derivative right here just can be interpreted as the limit. Don't forget this proof, write it down. The limit as h goes to 0 of f of x plus h. So that would be the integral from a to x plus h, f of t dt, minus f of x, which is the integral from a to x, f of t dt, all over h. I just did the definition of derivative. You should write this down, please. Okay, so this is f of x plus h. This is my function, see? So I just put an x plus h here. Minus f of x, all over h, just definition of derivative. Geometrically, what this means is there's this function called f of t, right? And we're integrating from a to x plus h, so that's all this area here. That's what this integral means in red. And then this integral in blue just means the area between a and x. See? So the difference between this and this, literally the subtraction between these, is just this little sliver of area right in here between x and x plus h. Okay, so this can be written now as one integral just one integral from x to x plus h. And as for that h on the bottom, I could write that as x plus h minus x. The same thing as h, right? So I know it's kind of silly that I wrote it that way, but I want to show you something. This right here looks a lot like the average value of a function formula that we learned. Integral over interval. See it? Boy, that looks like an average value, doesn't it? Okay, so the limit as h goes to 0 of the average value of f of x, or f of t, over the interval x plus h. So what you're looking at here is the average value function, or average value definition, that we learned a couple days ago. Like that. And according to the mean value theorem, there is at least one value of c such that this is equal to f of c. So now I'll simplify this a little more and write limit as x goes to 0 of f of c. The mean value theorem takes us from here to here. And this is true for at least one value of c in the interval x to x plus h. Oh, and I accidentally copied the limit wrong here. This should have said h goes to 0. I'll put it in red. That was my mistake there. Sorry. Okay, now, this means that somewhere between x and x plus h, there's a value called c. Okay? But if we let h go to 0, what happens to this interval here? What happens to x, the domain x to x plus h, if h is shrinking all the way to 0? This just collapses and becomes what? From x to x, right? This would become from x to x. In other words, all of this just collapses to f of x. So this just becomes f of x. Because h is shrinking, so x to x plus h becomes from x to x, which means x. Okay, that's kind of a sophisticated proof, but this is such a simple rule that I felt like, man, maybe we should at least have the proof for it in our notes. But most people don't know the proof, they just kind of use this. Let's practice a couple more. Why don't you try one? I said that if you have sine t over t dt and you're going from a to x and there's a d dx right here, I said you can just get away with plugging the x in for each t. So I said the answer to this is sine of x over x. It's that simple. Now you try one. That's not cost, that's cosine t. This is awfully easy. I never said a had to be 0 or anything. You can ignore the 100 completely. What's the answer?
Cosine x over e to the x.
That's right. It's cosine x over e to the x. Done deal. Notice that that value at the bottom does not matter at all. That could be 100 down there, or it could be 1,000,000 down there. It doesn't make any difference. Okay? As long as it's a constant, we're good.
Does x have to be bigger than the constant?
No. X does not have to be bigger than the constant. Good question. But the x has to be at the top. Let's try this one. What would you do if you saw this, and for some reason x was at the bottom, and let's say there's an e up here?
Well, switch them and then negate the.
Yeah, so let's say you're given this problem here, square root of t, I don't know, over tangent of t. Just making that up. I wrote tan of t because I thought you might think it was like tant or something. Tant. Okay? Tangent of t. This is supposed to be really easy. The only thing that's wrong with this problem is the x is at the bottom. Right? So we should probably flip that around. Okay, so what's the price you pay for switching the limits of a function, or of an integral? Putting the e at the bottom and the x at the top, what price do we pay for that? A negative pops up, right? You can just put it in the very front, save it for later. That does not change the integrand at all. Okay, now you're welcome to plug in the x wherever you see a t. Okay, so what's my answer to this one? Negative, right? Rad x over tan x. Okay, this is kind of a mysterious rule, it seems, but honestly, it's really not very hard to use, and we've proved it's true if you're willing to abide by proof. And I think tomorrow we need to talk about what would you do if this down here, right here, guys, what if this was like an x squared? Or what if this was an x at the bottom and this was like an x squared at the top? Like, what would you do then? There's sort of a reverse chain rule sort of thingy I'll show you tomorrow without proof. It's a little hard to prove. So you'll be getting a set of problems to practice tonight. Some of them are this simple. Some of them are more like this problem that we started off with, where you find the area under the curve. By the way, these are both fundamental theorem of calculus. This is called Fundamental Theorem of Calculus Part 2 for some reason. And this new one I just taught you, where you plug it in, that's called Fundamental Theorem of Calculus Part 1. Some people switch the 1 and 2 around, but there's two parts to the fundamental theorem. Have a great day.